You know the drill, right? You pull out your phone, open up a travel app, type in where you want to go, and boom, in just a few seconds, you've got a whole list of flight options. It feels like total magic. But what's happening behind the screen isn't magic at all. It's actually a really powerful way of thinking, one that solves some of the world's most complicated puzzles. So let's pull back the curtain and see how it works. I mean, seriously, think about it for a second. How on earth does a computer sort through thousands, maybe millions, of different routes and connections to find that perfect path for you? And it does it all before you even have a chance to get bored and switch apps? Well, that's the exact mystery we're going to unravel right now. All right, to really get our heads around this whole thing, we're going to start small. Let's invent a fictional airline and ask a very, very simple question that's at the heart of all this. Okay, so let's meet our airline for today. We'll call it Barbet Airlines. As you can see, it flies to a bunch of cities across India. Some cities have direct flights between them, others don't. This map just gives us a bit of a real-world feel for the problem we're about to tackle. And here it is. This is the fundamental problem. For any two cities Barbet Airlines flies to, let's say Delhi and Chennai, how can we possibly know if you can even get from one to the other? Maybe it's a direct flight, maybe you need one or two layovers. How does a computer figure that out from scratch? Now, if we want to solve this like a computer scientist, the very first step is going to feel a little weird. It actually means taking that map we just saw and basically ignoring it. We have to shift how we look at the problem entirely. This right here is the key insight. The actual geography, the distances between cities, where they are in a map, for our problem right now, none of that actually matters. The only thing we care about are the connections. Which city is connected to which? That's it. So when we record the network, this is what we're left with. It's not a map. It's just a simple list, a table of direct flights. Delhi goes to Varanasi. Mumbai goes to Kolkata. That's it. This simple list is the entire world our computer needs to see. And this way of representing connections actually has a formal name in computer science. It's called a graph. It's an incredibly powerful concept. You just think of the cities as dots or nodes, and the direct flights between them are the lines or edges. Just like that, we've turned a real-world travel problem into a neat mathematical object. Okay, so we've modeled our airline as a graph. That's a huge first step. But now what? How do we actually use this graph to find out if you can get from Delhi to Chennai? Let's look at how a computer would approach this. It really boils down to two big steps. First, we've got to store this graph information in a way the computer can actually read and work with. That's what we call a data structure. And second, we need to write a set of instructions, an algorithm, that can cleverly search through that data to find a path from any node A to any other node B. Did you catch that word in the second step? Efficient? That little word is a huge deal. See, it's not enough to just cook up any set of instructions. It has to be a good one, a fast one. But what does efficient really mean when we're talking about flights? And this gets us to the next massive challenge in this kind of problem solving. The speed at which you find an answer is often just as important as the answer itself. So, how well our algorithm performs really depends on the size of the problem. We can think about it with two numbers, n, which is the total number of cities, and f, the total number of flights. Obviously, as n and f get bigger and bigger, the problem gets way harder. The real question for a computer scientist is, how much harder? Does it get a little slower, or does it grind to a complete halt? And this is exactly why it matters. Because you, me, all of us, when we're booking a flight, we expect an answer pretty much instantly. An algorithm that finds the absolute perfect route but takes an hour to do it, it's completely useless. The real world demands speed, and that pressure is what drives the search for these super efficient algorithms. So far, we've just solved the simple yes or no question of, can I even get there? But as we all know from experience, real world travel is a whole lot more complicated. So let's start adding some of that real-world messiness back into the picture. All of a sudden, our nice, clean graph problem gets a lot trickier. Now it's not just about finding a path, it's about finding a feasible one. A flight from Delhi to Mumbai doesn't help you if it lands after your connecting flight to Chennai has already left. And then you have all these other rules, like maybe you can't have a layover longer than 4 hours. Each rule adds another layer of complexity. Oh, and it doesn't stop there. What about the biggest question of all? Cost. How do we find the cheapest route? Not just any route. That's a whole different ball game. Or what happens when a plane has to be grounded for maintenance? The airline has to shuffle everything around to make sure people can still get where they're going. Each one of these is another incredibly tough algorithmic puzzle built on top of our simple little graph. But here's the really cool takeaway. This whole approach, taking a complex real-world problem, modeling it as a network of nodes and edges, and then designing smart algorithms to search it, this isn't just for airlines. It is the fundamental thinking that powers so much of our modern world, from your social media feed to your GPS to how packages get delivered across the globe. And that's really the thought I want to leave you with. Once you start to see the world in terms of these graphs, these hidden networks of connections, you'll start seeing them absolutely everywhere. Think about it. Your friend groups on social media, the way information spreads online, even the power grid that lights your home. What other invisible networks are shaping your day, all being managed quietly in the background by algorithms just like the ones that book your flights? Thanks for joining me for this explainer.